Hello and welcome to this revision session for AQA A-Level Physics Paper 2 on nuclear physics. So in today's revision session we're going to look at how we can answer examination questions on A-Level Physics Paper 2, in particular nuclear physics. So if we're successful we can answer A-Level Physics examination style questions, assess our understanding on A-Level Physics and understand what topics we need to improve upon for A-Level Physics. So how should you prepare for this revision session? When you're completing your work in this revision session, divide your piece of paper into two sections. Make the section on the left hand side larger than the right hand side. In this section, write down your working out and answers to the questions in the revision session. When you're doing this, make sure you write your answers in full sentences and show your full working out. Whilst in the right hand side section, write down any piece of information which you find useful or any hints and tips on answering questions from this revision session. After the revision session, write up these notes into a revision sheet for you to use independently. So how should you be revising for your A-Level Physics? Well, the first step is to learn the key facts. So use the revision guides, the class workbooks, prep notes, textbooks to learn the key ideas of the course. You might want to write mind maps or write out notes yourself. The second step is to test yourself. So use things like Caboodle, Seneca and knowledge checkers to quickly test your own knowledge, and you may wish to do this from your own cue cards. The third step is to practice examination style questions. Use exam prep books, homework books, supervised study books, additional workbooks to answer exam questions and to mark your own work. Now you might wish to download your own examination past papers to do this. So your three steps are learn the key facts, then testing yourself, and then practicing exam style questions. Now in this revision session you're going to find three types of questions. The first types of questions are the general check questions. They're designed to probe your understanding of the key concepts of the topic. The second ones are the checkpoint questions. They're more challenging questions designed to place your knowledge and understanding of the topics into different contexts and applications. And then finally the assessment point questions, which are past paper exam questions which will mimic the types of questions found in public examinations. So let's have a look at some questions for nuclear physics. The first question says, in the early 20th century a series of experiments was carried out in which alpha particles were directed at thin metal foils. A simplified version of the apparatus used is shown. Describe the observations from these experiments and the conclusions that were made from these observations. So pause the video now, then unpause the video when you want to go through your answer. Right, in this question, what should you be aware about for the alpha particle scattering experiment? That most alpha particles went straight through or were undeviated, so therefore the atom is mostly empty space. A few alpha particles were deflected by small angles, so therefore very few alpha particles came straight back. So therefore that told us that there's a concentration of charge in the atom, and that's where the concentration of the mass of the atom is as well. The next question says, Rutherford's scattering experiment was done in an evacuated container. Explain why this is necessary. Then in the Rutherford's experiment, alpha particles were directed at thin gold foil. A small fraction of the alpha particles were backscattered through 180 degrees. Describe and explain how the fraction backscatter changes if the following changes are separately made. A thicker foil is used. Faster alpha particles are used. A silver foil is used. Now a silver nucleus has less positive charge but roughly the same volume as a gold nucleus. So pause the video now, then unpause the video when you want to go through your answer. Right, we needed to use an evacuated container as if there were air molecules in the container. The alpha particles would scatter off them and then distort the results, and the alpha particles could also be distorted by 6 centimeters of air. If a thicker foil was used, you get more backscattering because there's a greater chance of a closer approach to a gold nucleus, so therefore you get more of them reflecting backwards. If faster alpha particles are used, fewer will get backscattered because their inertia, because they've got a higher velocity, so therefore greater inertia, will tend to carry them forwards even if they are interacting with the gold nuclei. And if a silver foil is used, fewer will get backscattered because the positive charge of the nucleus is smaller, so therefore the repulsive force between the alpha particle and the nucleus would be smaller. The next question says, before Rutherford's model, scientists believed that the atom was made from negatively charged electrons embedded in a plum pudding of positive charge that was spread throughout the atom. Explain how the alpha particle experiment proved that this old model of the atom was incorrect. Then Geiger and Marsden carried out an experiment to investigate the structure of the atom. In this experiment, alpha particles were scattered by a thin film of gold. When Rutherford analysed their results, what conclusion did he draw about the distribution of mass and charge in the atom? Then describe and explain how the experimental observations that led to these conclusions. So pause the video now, then unpause the video when you want to go through your answer. Right, so in this first one, the plum pudding model predicts that there'll be no large angle scattering events. An alpha particle is more massive than an electron and won't be deviated by an electron. Now, the actual experiment shows that a few alpha particles will be scattered by more than 90 degrees. Now, alpha particles must have interacted with a charged object much more massive than an electron. This object contained most of the mass of the atom, so therefore was called a nucleus. Now, in the next one, what conclusions did he draw? Well, he concluded that most of the mass was concentrated in a small space, that this space, or the nucleus, was positive and surrounded by negatively charged electrons. Now, this was shown because most alpha particles passed through undeviated through the goal, so most of the atom was empty space. Some alpha particles were deflected through large angles, showing that part of the atom is much heavier than the alpha particle and positive, and the electrons were known to exist from J.J. Thomson's experiments, so other particles in the nucleus must have been positive and heavier, and the relative number of large deflections shows the size of the nucleus. The next question says, in Rutherford's alpha scattering experiment, most of the alpha particles were not scattered. What can you conclude about the nature of the atoms? State the approximate radii of the atom and of the nucleus. In a visual model of the atom, the nucleus is represented by an apple of diameter 8 centimeters. Estimate the diameter of the atom in this model, and then the figure below shows the path of an alpha particle close to the nucleus of lead. Draw arrows to represent the force on the alpha particle at A, at B, and at C. So pause the video now, then unpause the video when you want to go through your answer. Right, it shows us firstly that most of the atom is empty space because they move through undeviated. You've got to know the facts that the atom is 10 to the minus 10 meters and the nucleus is 10 to the minus 15 meters in terms of radii. So using this idea of the fact that the difference between the two of them is 10 to the 5 meters, therefore the diameter is going to be 8 centimeters times by 10 to the 5, that's the difference, so therefore it's 8,000 meters. And then this next one, you'll show that in each case the force arrows are always pointed towards the alpha particle from this, because the force on the alpha particle, and then the magnitude of the force is the largest to B, so you've got the longest arrow because they are the closest at that point. The next question says, alpha particles of kinetic energy 8.8 mega electron volts are fired at lead atoms. The charge of the nucleus and the lead is 82 E. Calculate the minimum distance the alpha particle approaches to the nucleus of the lead, the maximum electrostatic force experienced by the alpha particle, and then a tiny droplet of oil diameter 1 millimeter is placed on water. The oil spreads out as a circular disc of thickness approximately 1 atom thick. Estimate the radius of this oil disc. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we can say that you can work through that the force is equal to QQ times by 4 pi epsilon 0 r squared. That is, in fact, that's the electrical force equation learned in electrical fields. Now you can see that the value is going to be of the overall, sorry, the energy, not the force. Okay, that's the gravity. That's going to be the electrostatic potential energy. My apologies. So you can work out what that energy is because it's the kinetic energy of the alpha particle. Because the alpha particle's kinetic energy goes into the electrical potential energy when it gets close to the nucleus. So you can work that by doing 8.8 times 10 to the 6, so mega electron volts into electron volts, times by 1.6 times 10 to the minus 19. So therefore, that is then electron volts into joules. That's going to be equal to the electrical potential energy, so it's 1.4 times 10 to the minus 12. That equals QQ over 4 pi epsilon 0 r squared. You make r the subject because you know what Q and Q are. Remember again that Q for the alpha particle is 2 because there's 2 protons, 2 neutrons, and then the value of charge for the nucleus is 82. It tells you there, times both by 1.6 times 10 to the minus 19. Work it all through, and D is equal to 2.68 times 10 to the minus 14 meters. Now we know the electrostatic force from the electrical field's unit is going to be equal to QQ over 4 pi epsilon 0 r as working it through. So you pop all the values in, work it all out, and then you get your answer to be 53 newtons. Now again, we can see here that the initial volume is going to be equal to the final volume, so you can work that as 4 over 3 pi r cubed is therefore equal to, again, 10 times 10 to the minus 10 pi times by r squared. Work it all through, and r is equal to 1.3 meters. The next question says, the radioactive decay of nuclei is both random and spontaneous. Explain what is meant by radioactive decay, random decay, and spontaneous decay. So pause the video now, then unpause the video when you want to go through your answer. Right, what's radioactive decay's definition? It's the emission of alpha, beta or gamma particles from an unstable nucleus, trying to become more stable. Random decay indicates that it's impossible to predict which particular nucleus will decay. The rate of decay of many nuclei varies above and below the average value, and spontaneous decay means it's not affected by other nuclei or any other factors around it, so it's not affected by external conditions such as temperature. Now, radioactive decay, like we said, is both random and spontaneous. The next question says, explain why you would expect beta minus particles to travel further through the air than alpha particles. Explain why you would expect beta minus particles to travel further through the air through air than through metal. Then explain why the most strongly ionizing radiation, alpha particles, is the least penetrating, whilst the least ionizing, gamma rays, is the most penetrating. A smoke detector uses a source of alpha radiation to detect the presence of smoke in air. How does a smoke detector work? It suggests why an alpha source is more suitable for this than a beta minus or gamma source. So pause the video now, then unpause the video when you want to go through your answer. Right, so in the first one, a beta minus particle has less charge, it's smaller and it travels faster, so it's less likely to cause ionization of an atom, so therefore it'll travel further before it loses energy from this ionization process. It'll travel much further through air than through metal because air is much less dense than metal, so there's less ionization caused because there's less interactions with the atoms of the object. Now, more strongly implies that more strongly ionized implies that the radiation will have more collisions with the particles, so therefore there's a greater loss of momentum in each collision, so therefore will not travel as far, so there'll be less penetration. Now, for a smoke detector, alpha particles pass between two plates connected to electrical power supplies. The alpha particles cause ionization in the air between the plates, and therefore a small current will flow. When the smoke enters the device, the alpha particles are absorbed, and there's less ionization of the air, and there's a smaller current in the external circuit. The circuit then switches on the alarm. Alpha radiation is most suitable because it's most strongly ionizing. It causes a greater current to flow, and also alpha particles are more likely to be absorbed by the smoke. Also, the range of the alpha particles is so small that it's unlikely to constitute a hazard to the user. The next question says, a radioactive source emits beta minus particles. It has an activity of 2.8 times 10 to the 7 becquerels. Estimate the number of beta minus particles emitted in a time interval of 2 minutes. State one assumption made. Then a sample of 1,000 undecayed nuclei of a nuclide whose decay constant is 0.20 seconds to the minus 1. Determine the initial activity of the sample. Estimate the activity of the sample after 1 second. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we know that the number of particles is equal to A, the activity, times by the change in time. So therefore it's 2.8 times 10 to the 7 times by 120 seconds, minutes into seconds. So we get 3.4 times 10 to the 9 beta particles, and that's assuming that the activity remains constant. Now, in this next one, we also know activity is equal to the negative of the decay constant times by n. So it's 0.20 times by 1,000 is equal to 200 seconds to the minus 1 or 200 becquerels. So therefore, after 1 second, 200 of those nuclei will decay, so 800 will be left. So the activity after 1 second is going to be A times by the change in time, so therefore so the decay constant times by the number, my apologies, so the decay constant 0.2, the number is now 800 because 200 have decayed from 1,000, so we get 160 or seconds to the minus 1 or 160 becquerels. The next question says, a sample of carbon-15 initially contains 500,000 undecayed nuclei. The decay constant for this isotope of carbon is 0.3 seconds to the minus 1. Determine the initial activity of the sample. A small sample of radium gives a received count rate of 20 counts per minute in a detector. It is known that the counter detects only 10% of the decays from the sample. The sample contains 1.5 times 10 to the 9 undecayed nuclei. Determine the decay constant of this form of radium. Then a radioactive sample is known to emit alpha, beta and gamma radiations. Suggest 4 reasons why the count rate measured by a Geiger counter placed next to the sample will be lower than the activity of the sample. So pause the video now, then unpause the video when you want to go through your answer. Right, again, in this first one, activity is the decay constant times by the number of nuclei, so 0.3 times by 500,000, 150,000 per second. Next one, activity is equal to 10 times by the count rate of the detector, because it's going to be 10 times by the number you got there, so it'll be 10 times by 20 per minute, so therefore it's going to be 200 per minute, so therefore in seconds it's going to be 200 divided by 60, so therefore work it all through, it's going to be approximately 10 over 3 when you work it through, so therefore decay constant is A times by N, which we looked at previously, so therefore, A over N, my apologies, so you work it all through and you get 2.2 times 10 to the minus 9 seconds to the minus 1. Now the activity is always higher than the count rate because gamma rays are not always detected because they're very weakly ionizing. The counter will always have some inefficiencies. Some radiation will be absorbed within the sample before it actually gets out and reaches the detector, and the detector is directional, so some radiation will move away from the detector rather than towards it because it won't completely surround the source. The next question says, suppose that we start an experiment with 1 times 10 to the 15 undecayed nuclei of an isotope for which the decay constant is equal to 0.02 seconds to the minus 1. Determine the number of undecayed nuclei after 20 seconds. The isotope nitrogen-13 has a half-life of 10 minutes. The sample initially contained an 8 times 10 to the 10 undecayed nuclei. Write down an equation to show how the number undecayed, n, depends on the time. Determine how many nuclei will remain after 10 minutes, then after 20 minutes. Determine how many nuclei will decay during the first 30 minutes, and then a sample of an isotope for which the decay constant is 0.10 seconds to the minus 1 contains 5 times 10 to the 9 undecayed nuclei at the start of an experiment. Determine the number of undecayed nuclei after 50 seconds and its activity after 50 seconds. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we know that n is equal to n0 e to the minus lambda t. So therefore, it's 1 times 10 to the 15 times by e to the power minus 0.02 times by 20 the time. So therefore, you get 6.7 times 10 to the 14 nuclei. So again, our equation is n equals n0 e to the minus lambda t. So after 10 seconds, you know that half the nuclei will decay because it's got a half-life of 10 minutes. So therefore, it's 8 times 10 to the 10, half, so it's 4 times 10 to the 10. After a further 10 minutes, the next half will decay. So you've got a quarter left, so 2 times 10 to the 10. After 30 minutes, 3 half-lives have elapsed. So therefore, it's halved 3 times. So therefore, what you can say is the number of original nuclei decaying will be a half, then a quarter, then an eighth. So therefore 7/8 will have decayed and an eighth will be left. So 7/8 of 8 times 10 to the 10 is 7 times 10 to the 10. The next one, you would say n equals n0 e to the minus lambda t. Pop in all the values, you get 3.4 times 10 to the 7. And then again, activity is lambda times by n. We know 0.10 is lambda. We've got n from the previous question, so we get 3.4 times 10 to the 6 becquerels. The next question says, below shows the decay of a radioactive isotope of cesium. Use the graph to determine the half-life of this nuclide in years and then find the decay constant in years to the minus 1. The decay constant of a particular isotope is known to be 3 times 10 to the minus 4 seconds to the minus 1. Determine how long it would take the activity of a sample of this substance to decrease to 1/8 of its initial value. So pause the video now and unpause the video if you want to go through your answer. Right, we can tell from the graph the half-life is the time it takes to half, so we go from 400 to 200. So therefore, that's 2.4 years. Decay constant is natural log 2 over the half-life, so therefore it's 0.29 years to the minus 1. Now you can see here how long it would take to go to 1/8 of its value. So 1/8 if its value is 3 half-lives, because 1 half-life to a half, second half-life to a quarter, third half-life to an eighth. So that's a very important idea. So therefore, what is 3 half-lives? Well, it's 3 times by the half-life, which we can say to be 2.4 years. So we can work it all through. So it's 6.9 times 10 to the 3 seconds. In our next question, an isotope of N decays with a half-life of 7.4 seconds. Calculate the decay constant for this nuclide. Then a sample of N contains 5,000 nuclei. Determine how many remain after a time of 14.8 seconds and then 20 seconds. Then a sample contains an isotope of half-life t to a half. Show that the fraction of the nuclei in the sample which remain undecayed after time t is given by the equation f is equal to a half to the power n, where n equals t over half-life. Calculate the fraction f after the following times: 1 half-life, 2 half-lives, 2.5 half-lives, and 8.3 half-lives. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first question, how do you work it through? Well, in the first one, we know that the decay constant is going to be equal, okay, to when we're working it through, it's going to be equal to log 2 over the value. So it's log 2 over 7.4, 0.94 seconds to the minus 1. Then the next one, n equals n0 e to the minus lambda t. So it's 5 times 10 to the 3 times by e to the power minus 0.094 times by 14.8 is 1250. After 20 seconds, same thing, 760. Now in the next one, we can say we can find an expression for the decay constant which we can sub into the decay equation. So the quantity F is going to be the ratio of the atoms remaining to decay to the original atoms of the sample. So we can say F equals n over n0, where t equals a half-life. So therefore F is therefore going to be equal to a half equals e to the minus lambda t over the lambda t, which t is a half-life. So take natural logs of both sides. So therefore we can say F is therefore equal to e to the power log a half times by t over the half-life. We can then work it all through, so F equals a half to t to the power, the half to the power of t over the half-life. So after one half-life, a half is remaining. After two half-lives, a quarter is remaining. After 2.5 half-lives, 0.18 are remaining. And then finally, after 8.3 half-lives, 0.032 is remaining. The next question says the initial activity of a sample of 1 mole of Radon 220 is 8.02 times 10 to the 21 seconds to the minus 1. Calculate the decay constant for this isotope and the half-life for this isotope. The figure below shows the count rate recorded when the sample of the isotope indium-116 decays. Use the graph to find the half-life of the isotope and calculate the decay constant. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we know that A equals a decay constant times by n. So decay constant is A over n. We've got A, we've got n, because we've got 1 mole, so it's 6 times 10 to the 23 particles in 1 mole, so it's 1.33 times 10 to the minus 2 seconds to the minus 1. Half-life is log 2, or 0.693, divided by the decay constant, which just worked out, so it's 52 seconds. In this next question, from the graph, a half-life is the time it takes to go from 160 to 120, so that's 28 seconds. So therefore, so you can work it through, okay, to find the half-life, it's going to be 14 seconds. Now this next one here, okay, we'll consider the decay constant is going to be the half-life times equals log 2 over the decay constant, so that's log 2 over 14, which we just worked through, so it's 4.95 times 10 to the minus 2. The next question says the proportion of different isotopes in rocks can be used to date the rocks. The half-life of uranium-238 is 4.9 times 10 to the 9 years. A sample has 99.2% of the proportion of this isotope compared with the newly formed rock. Calculate the decay constant for this isotope of uranium and calculate the age of the rock. Then the figure below shows how the randomness affects count rate. State and explain what happens if the experiment is performed using the same amount of radioactive material but at a higher temperature. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we can see that the half-life is equal to log 2 over the decay constant. We've got the half-life, so we can work it through, so it's 1.4 times 10 to the minus 10 years to the minus 1. The age of the rock is going to be equal to n is equal to n0 e to the minus lambda t. So we can rearrange that and say log n over n0 equals minus lambda t. So therefore we can work through t with all the values. Remember, 99.2% means n over n0 is 0.992. So therefore time is equal to 5.7 times 10 to the 7 years. Now in this next one, there'll be no change in count rate because radioactive decay is spontaneous, so temperature does not affect the count rate or the radioactive decay of the substance. The next question says an isotope of carbon-14 emits a beta-minus particle and changes to an isotope of nitrogen. What are beta-minus particles? Write a nuclear decay equation for this decay. Draw a graph with the y-axis representing the nucleon numbers between 10 and 16 and the x-axis representing the proton numbers between 4 and 10. And on the graph, mark the isotope for carbon and the daughter nucleus that this decay would produce. So pause the video now, then unpause the video when you want to go through your answer. Right, beta-minus particles are fast-moving electrons, and this is important for every nuclear decay that they come from the nucleus themselves. So you can see the decay equation here. Remember, the antineutrino is needed to conserve the lepton number in this decay. Then here you can see our graph here, and you can see firstly the carbon isotope. Now you can see that it turns into nitrogen. Now you can see straight away the proton number goes up by 1, turn it into nitrogen, but the overall number stays the same, because as you can tell in the beta minus decay that a neutron turns into a proton, so the overall number of protons and neutrons, the nucleon number, stays constant. The next question says the nuclide of lead 210 decays into three separate stages by alpha and beta minus emission to another nuclide 206 pb. So describe the structure of 210 pb, and then alpha minus and beta minus particles. So alpha and beta minus particles are known as ionizing radiation. State and explain why such radiations can be described as ionizing. And then the two lead nuclides are shown in the graph of nucleon number A against proton number Z. Copy the graph and draw 3 arrows to represent one possible route for the 3 decays between the 2 isotopes of lead. Label each arrow to show whether it's an alpha particle or a beta minus particle emitted. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we can see that the number of protons is 82 because it's the lower number, and the number of neutrons is 128 because it's 210 minus 82. Now in this next one, they are ionizing radiations because the particles are charged, so when they collide with or they pass close to other atoms, they'll knock electrons from the atoms and leaving behind those charged atoms or ions, so ionization. In this next one, you can see a possible path here, so you can see you could either have beta minus, and then you could have alpha, or you could go with alpha, beta minus, and you can see the path that it shows. Remember, one alpha decay will lose the nucleon number of 4, okay, but then if you actually look on the value for Z, it'll go down by 2, and then whilst when you here you've got beta minus, it'll stay constant for the nucleon number, but then the Z number, the proton number, will go down by 1 each time. So the next question says, calculate the nuclear radii in femtometers of the following: helium, lithium, iron and uranium. Then how does the nuclear density for uranium compare to that of helium? And then the neutron star of mass 4 times 10 to 30 kilograms has a radius of 12 kilometers. Calculate its mean density and comment on the answer. So pause the video now, then unpause the video when you want to go through your answer. Right, the equation to work out the nuclear radius is R0 a to the power of a third. So you can do R0 as 1.2 in terms of femtometers. So therefore it's 1.2 times by 6 to the power of a third, which is the nucleon number. So it's 2.2 femtometers. The next one 2.5 femtometers. The next one 4.6 femtometers. And the next one 7.4 femtometers. Now you can work out density by doing mass over volume. So you can work out the mass by multiplying the nucleon number by 1.661 times 10 to the minus 27, which is converting the nucleon number into kilograms. Then you can divide it by the volume, which is 4 over 3 pi r cubed. So you can work out the radius of each one from the femtometers given previously. Remember, femtometers is 10 to the minus 15. So you can work it out from the previous information, and you get 2.3 times 10 to 17 for both densities. And that's an important idea, that the nuclear densities for every nucleus of every element is the same. Now in this next one, density is mass over volume. So you've got your mass there, you've got your radius of 12 kilometers, turn that into meters and do 4 over 3 pi r cubed. Work it through and you get 5.5 times 10 to 17, which is similar to the density of a nucleus. The next question says gold has a density of 19,700 kilograms per meter cubed. A mass of 193 grams of gold contains 6.02 times 10 to 23 atoms. Use this information to estimate the volume of a gold atom and hence its radius, and state any assumptions that you make. So pause the video now, then unpause the video when you want to go through your answer. Right, in this question, we know that density is mass over volume. So 193 grams of gold occupy a volume of mass over density. So you can work that through to be equal to be 9.8 times 10 to the minus 6 meters cubed. Remember, we turned out grams into kilograms in this question. So the volume occupied by one atom is therefore the volume of 193 grams divided by the number of atoms in 193 grams. So therefore we can work it through with Avogadro. So we've got the idea of working this idea to be 1.6 times 10 to the minus 29 meters cubed. So therefore the volume of one atom is going to be 4 over 3 pi r cubed. So therefore we can rearrange that, make r the subject, and so therefore it's going to be equal to 1.6 times 10 to the minus 10 meters. And our assumption is that there's very little space between those atoms, okay, in that mass. The next question says that this question is about the nucleus of uranium-235, which has a mass of 3.89 times 10 to the minus 25 kilograms. In this information, state the number of protons and neutrons in the nucleus. The radius of a nucleus is given by the equation R equals 1.41 times 10 to the minus 15 times by 8 to the power of a third. Determine the density of the uranium nucleus, then explain why the total mass of the nucleons is different from the mass of a uranium nucleus, and then without calculation, explain why you can determine the binding energy per nucleon for uranium-235 from its mass and the masses of a proton and a neutron. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, the number of protons is 92, it's the lower number. Number of neutrons is 143, 235 minus 92. In this next one, we can work out the volume. The volume is 4 over 3 pi r cubed. So therefore, what is our volume going to be? Well, we can work it all through and we can see that it's going to be equal to 2.76 times 10 to the minus 42 meters cubed. Therefore, we can use that to then work out what r is going to be by looking at the idea of linking in volume into when we link it into the mass as such like that. So we get 1.4 times 10 to the 17 kilograms per meter cubed. Now the mass is going to be different because when the nucleons are combined in a nucleus, they have less energy than when they're separated. Now less energy means less mass because energy has mass, so therefore the mass will be lower when they are in a nucleus. In the next one, if you sum the total mass of the separate protons and neutrons, then you subtract that from the mass of the overall uranium nuclide, you can then work out what the energy is when it goes into a nucleus by doing the energy is equal to the change in the mass between the separate protons and neutrons and the nucleus times by c squared, and this change of energy is known as the binding energy. Now the next question says approximate values for the radius of a gold atom and the radius of a gold nucleus are 10 to the minus 10 meters and 10 to the minus 15 meters respectively. Estimate the ratio of the volume of a gold atom to the volume of a gold nucleus. And then the density of gold is 19,000 kilograms per meter cubed. Estimate the density of a gold nucleus and state any assumptions that you make in your answer. So let's have a go, see if we can work it through. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we know the volume of a sphere, which we assume an atom to be, and a nucleus to be 4 over 3 pi r cubed. So therefore the ratio of the volumes is 10 to the minus 10 cubed over 10 to the minus 15 cubed, which leads us to a ratio of 10 to the 15. Now the next question is 10 to the 5 cubed, which is 10 to the 15. Now in this next one, if we assume that most of the mass of the atom is contrary to the nucleus, then 19,000 kilograms of gold has a volume of 1 meter cubed. From A1, the volume of a nucleus has with this mass is 1 times 10 to the minus 15 meters cubed. So therefore, the density of gold is going to be 1.9 times 10 to the 4, divided by, of the nucleus, 1.9 times 10 to the 4, which is given in the previous information, divided by 10 to the minus 15, so therefore it's 1.9 times 10 to the 19 kilograms per meter cubed. The next question says the sun releases vast amounts of energy. Its power output is 4 times 10 to 26 watts. Estimate how much its mass decreases each second because of this energy loss. Then calculate the energy released if a helium nucleus is formed from separate protons and neutrons. The masses are given in the table below. Calculate the energy released per nucleon. Then a golf ball has a mass of 150 grams. Calculate its increase in mass when it's travelling at 50 meters per second. What is its percentage of its rest mass? So pause the video now, then unpause the video when you want to go through your answer. Right, in this question, E equals mc squared. So this gives us the mass decrease per second. So m equals E over c squared. We know E per second is 4 times 10 to the 26 because what's our energy per second? Divided by c squared, 3 times 10 to the 8 squared. So it's 4.4 times 10 to the 9 kilograms. We know helium nuclei are formed from 2 protons and 2 neutrons. The energy released is the difference in mass between the 4 separate nucleons and the helium nucleus. So if you work out this difference in the masses, it's going to be 5.04 times 10 to the minus 29 kilograms. E equals mc squared, so pop that into the E equals mc squared equations, and our energy is 4.5 times 10 to the minus 12 joules. So what's the energy released per nucleon? Well, there's 4 of them, and there's 4.5 times 10 to 12 over 4 of them, so therefore it's 1.1 times 10 to the minus 12 joules. In this next question, the kinetic energy of a golf ball is a half mv squared, so it's a half times by the mass in kilograms, 0.150, times by 50 squared is 187.5 joules. The mass energy equivalent of the ball is going to be equal to m equals E over c squared, so it's 187.5 over c squared, 2.1 times 10 to the minus 15 15 kilograms. So find the difference as a percentage of its rest mass, which is 0.150 kilograms. So it's 1.4 times 10 to the minus 12%, which is about right for an object on the real world scale. The next question says the mass of an atom of iron is 55.934937 U. Calculate its mass in kilograms. Then the mass of an atom of oxygen is 2.656015 times 10 to the minus 26 kilograms. Calculate its mass in U. The table below gives the mass in U of several nuclides. Determine the mass excess of helium, and then one nuclide has a negative mass excess. Name the nuclide and determine its mass excess. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, how can you convert from U into kilograms? Multiply by 1.661 times 10 to the minus 27, so it's 9.2880 times 10 to the minus 26 kilograms. We can reverse it by dividing by 1.661 times 10 to the minus 27, so it's 15.995 U. In this next one, the mass excess is the mass of the helium nucleus minus the mass of the four separate nuclides, so it's 0.002602. The mass excess of potassium is a negative, so therefore it's 0.036002. The next question says a nucleus of beryllium decays into an isotope of boron by beta minus emission. The chemical symbol for boron is B. Write a nuclear decay equation for the nucleus of beryllium-10 and then calculate the energy released in this decay and state its form. So pause the video now, then unpause the video when you want to go through your answer. Right, the nuclear decay equation is beryllium will go into boron, and you'll have an electron because you notice the proton numbers are going up by 1, the nucleon numbers stay constant, so the only thing that can conserve those numbers is an electron. The next one, the mass difference, is the difference in mass between the beryllium at the start and then the boron and the electron. So you can find the difference to be 9.89044 times 10 to the minus 31 kilograms. So therefore the energy release is E equals mc squared. So you get 8.9 times 10 to the minus 14 joules. And this tends to be released as the kinetic energy of the products in this particular decay. The next question says, in a nuclear reactor, the mass of uranium and the fission fragments fall to a rate of 70 micrograms per second. Calculate the maximum power output from the reactor, assuming it's 100% efficient. The equation below shows the radioactive decay of Radon 222. Calculate the total energy output from this decay and state what forms of energy are produced. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we know E equals mc squared, so 70 times 10 to the minus 6 times by 3 times 10 to the 8, so every second you've got an energy being released of 6.3 times 10 to the 9 joules. The energy per second is the power, so that is the answer, so it's 6.3 gigawatts. In the next one, we know the mass deficit is going to be equal to the mass of the radon minus the mass of the plutonium, the alpha particle, and the gamma, but obviously there's no mass for the gamma. So you can work that through and you get your difference to be 0.005 U. We can convert that into kilograms by multiplying by 1.661 times 10 to the minus 27. So it's 8.3 times 10 to the minus 30 kilograms. Energy released E equals mc squared. Pop it through and you get 7.47 times 10 to the minus 13 joules, and that'll be is kinetic energy of the alpha particle, and because you've got a gamma ray, some of the energy will go as the gamma ray as well. The next question says calculate the binding energy per nucleon for the nuclide iron, and then the mass of beryllium nucleus is 1.33 times 10 to the minus 26 kilograms. A proton and a neutron have a mass of about 1.67 times 10 to the minus 27 kilograms. For the nucleus of beryllium, determine the mass defect in kilograms, the binding energy, and the binding energy per nucleon. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first question, the mass of the neutrons is going to be 56 minus 23, so it's 30 for the iron. So find the mass defect by doing the mass of the protons and the mass of the neutrons, and then subtract it from the overall mass of the nucleus. So you get 8.680 times 10 to the minus 28 kilograms. Binding energy is E equals mc squared. Pop all the values in, and you get 7.812 times 10 to the minus 11 joules. We can then divide it by the total number of nucleons, the large number on the symbol, so 56, so it's 14 times 10 to the minus 13 joules. In the next question, the mass defect is going to be the number of protons and the number of neutrons in beryllium, which is 4 and 4, minus the mass of the beryllium. So it's 6 times 10 to the minus 29 kilograms. The binding energy, so you multiply that by c squared. So you get 5.4 times 10 to the minus 12. You can divide that by 1.6 times 10 to the minus 19 to get into EV. So it's 3.4 times 10 to 7 EV. So the binding energy per nucleon is then that value divided by the number of nucleons, which is 56, which is going to be 8. So therefore it's 6.8 times 10 to the minus 13 joules, or 4.2 times 10 to 6 EV. The next question says, explain why hydrogen does not appear on the graph below, and then using the binding energy graph below, suggest why fission is unlikely to occur with light nuclei and why fusion is unlikely to occur for heavier nuclei. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we can see that hydrogen is a single nucleon, so therefore it can't have a binding energy because the binding energy is the energy lost by the nucleons as they go into a nucleus. And then the second one, fission for lighter nuclei is unlikely because the products of the fission have a smaller binding energy per nucleon, so be less stable, and then the reaction therefore would require an input of external energy, and then for fusion it's unlikely for the same reason as well. The next question says, a carbon-12 atom consists of 6 protons, 6 neutrons, 6 electrons. The unified atomic mass unit U is defined as 1/12 of the mass of a carbon-12 atom. Calculate the mass defect in kilograms, the binding energy, and the binding energy per nucleon. So pause the video now, then unpause the video when you want to go through your answer. Right, so the mass defect is going to be the mass of the individual components minus the mass of the nucleus, so you get 0.098934 U. Multiply that by 1.661 times 10 to the minus 27 to get it in kilograms to be 1.64 times 10 to the minus 28 kilograms. Multiply that by c squared to get the binding energy, so it's 1.48 times 10 to the minus 11 joules. Divide that then by the number of nucleons, which is 12 because you've got 6 protons and 6 neutrons. Electrons are nucleons. So you get 1.23 times 10 to the minus 12 joules. The next question says the fusion reaction which holds the most promise for the generation is the fusion of tritium and deuterium. The equation below shows the process. So calculate the change in mass in this reaction, the energy released in this reaction, and the energy released of 1 mole of deuterium reacted with 1 mole of tritium. So pause the video now, then unpause the video when you want to go through your answers. Right, the change in mass is going to be equal to the mass of the things at the start, so be tritium and deuterium, minus the mass of the helium and the mass of the hydrogen after the end. So we get our difference to be 0.020271 U. Multiply that by 1.661 times 10 to the minus 27 to get into kilograms to be 3.365 times 10 to the minus 29 kilograms. Multiply by c squared to get the energy release, so it's 3.028 times 10 to the minus 12 joules. And then if we want, that's the energy released per atoms, the energy released per mole, with that multiplied by Avogadro's constant, the number of molecules in 1 mole. So we multiply that by Avogadro and we get 1.823 times 10 to 12 joules. The next question says, a student supervised by their teacher carries out an experiment with 3 unlabeled radioactive sources. The student is told that each source emits only one type of radiation. One emits gamma, one emits beta minus, one emits beta plus particles. The student has the following equipment: a selection of materials of different thicknesses, a strong magnet, and a radiation counter. Explain how the student can use this equipment to determine safely which radiation each source emits. So pause the video now, then unpause the video when you want to go through your answer. Right, so what method would you use? So you'd measure the background count and subtract from your source count, very important in any radioactive experiment. You'd clamp the source pointing away from you. You'd have safety precautions, so like handle the source with tongs, limit the time of exposure. You'd record the count over a fixed period and then investigate how the count rate varies with the range. You could place aluminium sheets between the source and radiation counter. You could then set up magnetic fields at right angles to emission direction to investigate if they deflect as charged particles, or you can move the radiation counter to find the direction of the deflection. Now you should note that gamma has the longest range in air, beta minus and beta plus have a similar range. Gamma will penetrate aluminium, which is a few millimeters thick, but beta will not. Gamma is undeflected by a magnet because it's neutral, but beta radiation is deflected by a magnet because they are charged. Beta plus and beta minus, as they're oppositely charged, will deflect in opposite directions in a magnetic field. And then you can use Feynman's left-hand law to actually determine the charge on whether it is a positron, the beta plus, or the electron, the beta minus particle. And then also remember as well, with beta plus, the current is in the same direction as the motion because it's a positively charged particle, so you can see it as if it was conventional current. The next question says, in beta plus decay, a proton decays into 3 of the particles. Write the nuclear equation for this process, and then a student supervised by a teacher carries an experiment with the 3 unlabeled radioactive sources as indicated before. So, explain how you can use this equipment safely to determine the radiation emission. So in this first one, it is going to be a proton will go to a neutron, and then you're also going to have your neutrino will be present as well, okay, and also your positron will work also. Now the next question says the student gathers the following data and plots the following graph of data. The half thickness value x for a particular shielded material and type of radiation is often used in industry, and the value of the thickness of the shielding required to reduce the incident of the radiation by half. The student thinks that the relationship shown by the data of the corrected count versus the shielding is exponential. Use the information provided and describe a form of mathematical test to support this conclusion. Calculate the half thickness, describing also the method you would ensure a reliable value. So pause the video now, then unpause the video when you want to go through your answer. Right, in this one, how could you use the data? So the data from the table could be used to find the constant reduction factor between the successive points. So you should do multiple data points and find that you've got a constant value. Or you could do a natural log value for each count rate, and then the difference between the successive values is calculated and found to be constant. So that's how you can determine exponentiality, either with using natural logs or from taking the values and finding the rate of change, and the rate of change should be constant. In terms of using the graph, the count rate decreases with increase in thickness. The relationship does show exponential decrease of count rate, and there because it shows the count rate halves at regular intervals with that of shielding. The thickness for the count rate should be dropped by the same fraction as it changes each amount of time, and the gradient of the curve at different thicknesses shows it halves at roughly regular values. You should find from the graph that the half thickness is at about 2 centimeters. You can use the graph to take measurements of values of half thickness. You should take multiple measurements to take an average value, so you can work it all through with your precision to be about 2.1 centimeters. The next question says, the cesium is a radioactive isotope produced during the fission of uranium. State what is meant by fission, then cesium decays by emitting beta radiation. Complete the nuclear decay for cesium. Explain why the emission of an antineutrino in the decay leads to a range of energies for the beta minus particle. Cesium is a major source of radiation from radioactive waste. A nuclear fission reactor produces about 24 kilograms of cesium each year. A website states that 24 kilograms of cesium has the same activity as 2,000 kilograms of radium. Assess whether this statement is correct, and then cesium may enter plants grown in a contaminated area. The radiation from 100 grams of plant material grown in a contaminated area can have a count rate as high as 500 becquerels. As a count rate of 150 per minute is considered safe, determine the time taken for the count rate from 25 grams of plant material grown in a contaminated to fall to a safe level. So pause the video now, then unpause the video when you want to go through your answer. Right, so what is meant by fission? That is when a massive nucleus splits into 2 or more smaller fragments of roughly equal mass, and you'll also produce some neutrons as well. Now in this particular equation, you can see that the cesium is 13555, the barium's gone up by 1 proton, so it's 56. You then got your beta minus is 0 minus 1, and your antineutrino is 0 0. It has no charge, so that all the values are conserved. Why do you get a decay? Well, because momentum is therefore conserved. The energy released is shared between the beta minus and the antineutrino, and therefore it's shared between a multiple number of particles in the decay, so it varies it out. In this next one, we know that the number of particles is 24 over 136.9 times by 1.66 times 10 to the minus 27. That's the mass of one particle. So therefore, it's 1.0 times 10 to 06 times 10 to the 26 particles. We know that the decay constant is log 2 over the activity, which is therefore going to be, so the half-life, my apologies, which is 30.2 times by 3.15 times 10 to the 7, because we work in seconds, not years. So it's 7.29 times 10 to the minus 10 seconds to the minus 1. So activity is lambda n. So therefore we've got lambda, we've got n, multiply the two together, and we get 7.73 times 10 to 16 becquerels, which is not equal to 7.3 times 10 to 16 becquerels, so it's not correct. In the next question, we know A is equal to a quarter of the initial, because if we look down, we can see how long it's taken to drop there. So time taken to drop is going to be, it's quartered, so therefore it's going to be a quarter of the initial, so 125 becquerels. So therefore, in terms of in seconds, that's therefore going to be 2.5 in your activity, because you know it's 150 count rate per minute, so therefore per second is 2.5 becquerels. So therefore we can do A equals A0 e to the power minus lambda t, pop in all the values. We can then use that to work out what lambda is, and therefore t is going to be 5.37 times 10 to the 9 seconds. The next question says, radon is a radioactive gas and emits alpha particles. Explain what is meant by the activity of a radioactive source and give its unit. The half-life of radon is 3.3 times 10 to the 5 seconds. Determine the time it takes for a sample of radon to decay to 20% of its initial activity, and then discuss the extent to which alpha particles are a risk to the human body. So pause the video now, then unpause the video when you want to go through your answer. Right, so in this first one, the definition of activity is the rate of decay, or the number of decays per second of the nucleus, and it's measured in becquerels. We know for the next one that the decay constant is log 2 over the half-life. So we've got the half-life in seconds, so we've got the decay constant to be 2.1 times 10 to the minus 6 seconds to the minus 1. We can say that A equals A0 e to the minus lambda t, so therefore e to the lambda t is A over A0, so you can work out what t is to therefore be 7.7 times 10 to the 5 seconds, or 8.9 days. Now, alpha particles are safe outside the body because they're stopped by skin. They're only dangerous if inhaled or swallowed, but they are highly ionizing, so if they are swallowed they can damage DNA, kill cells, cause cancer and cause radiation poisoning. The next question says, potassium-40 is a radioactive isotope and can decay by beta minus emission. Complete the nuclear decay, so the equation for the decay of potassium by beta minus emission, and then occasionally potassium decays by emitting a beta plus particle. Give two similarities between the beta minus and the beta plus particle. A fertilizer contains potassium chloride. The activity of a sample of the fertilizer reduced to radioactive potassium is 48.6 becquerels. It's claimed that the time t for the activity of a sample to fall below the background count rate will be more than 9 times 10 to the 9 years. To deduce whether this claim is correct. The background count is 0.42 becquerels and the half-life of potassium is 1.25 times 10 to the 9 years. So pause the video now, then unpause the video when you want to go through your answer. Right, we should know that if in this next one we know that calcium has 20 and by beta minus emission it's gained a proton, so potassium must be 19, but the overall nuclear number stays the same, so calcium has 40, and we also know that beta minus particle is always 0 minus 1. Now we know that beta minus and beta plus are particles and antiparticles, so they'll have the same mass, they're both leptons, they're both fundamental particles, they'll have the same magnitude of charge, they'll both be deflected in electrical and magnetic fields, and they'll both have the same ionizing power. Now in this next one we know the decay constant is log 2 over the half-life, so the decay constant is 5.55 times 10 to the minus 9 years to the minus 1. We can then work out what time is going to be by saying A equals A0 e to the minus lambda t, rearrange that, make t the subject, and we get 8.56 times 10 to the 9 years. The next question says that cesium-137 is a common product of uranium fission. Very small samples of cesium can be used to calibrate radiation detector equipment. Cesium decays to an isotope of barium by emitting a beta minus particle. Complete the nuclear equation for the decay of cesium. Then a sample of pure cesium has an activity of 7,400 becquerels. Calculate the mass in kilograms of the sample. So pause the video now, then unpause the video when you want to go through your answer. Right, in this one again, we know that by this decay, that cesium has lost a proton, so therefore it's going to be 55, the same number of nucleons, 137, beta minus, 0 minus 1, and again it's the same process going through here, except now we're looking for mass, so how we could work it through is do decay constants log 2 over the half-life, so we work out the half-life in seconds, so 7.29 times 10 to the minus 10 seconds to the minus 1. We know that n is going to be equal to the activity reactivity over the decay, over the half-life. So therefore you can work it, sorry, not the half-life, the decay constant. So therefore it's going to be 7,400 over the decay constant is 1.02 times 10 to 13. Then we can work out what the mass is, because we know the mass is going to be the number of particles times by the number of nucleons that we have, multiplied by 1.661 times 10 to the minus 27 kilograms. So it's 2.31 times 10 to the minus 12 kilograms. The next question says, a nucleus of thorium-230 is unstable and decays to a nucleus of radium-226 by emitting an alpha particle. The table shows the masses of the particles involved. Determine the energy in joules released when a nucleus of thorium-230 emits an alpha particle. Then determine the time taken in years for 90% of the thorium in the sample to decay to radium. The half-life of thorium is 75,400 years. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we can say, right, E equals mc squared. Now, mass is going to be the difference in the mass between the thorium and the radium. Okay, and also you can see that the alpha particle is also produced. So therefore, it's 5.1 times 10 to the minus 3u. Multiply that by the conversion factor to turn that into kilograms, 8.47 times 10 to the minus 30. So E equals mc squared. So 7.62 times 10 to the minus 13 joules. We know that the decay constant is log 2 over the half-life. So we can see that's 9.19 times 10 to the minus 6 years to the minus 1. We can then say A equals A0 e to the minus lambda t, but we can go A over A0 and equals e to the minus lambda t. Now, because it's lost 90% of it, therefore what's left is 10%, so therefore A over A0 is 0.1. Pop in all the values, we get out t to be 2.51 times 10 to 5 years. In the next question, in 1935, Irene and Frédéric Joliot-Curie were awarded a Nobel Prize for the discovery of artificial radioactivity. They bombarded an aluminium sheet with alpha particles to produce a radioactive isotope of phosphorus as in the nuclear equation below. Identify particle X, calculate the energy released in joules of this nuclear reaction, and then radioactive phosphorus was one of the first artificially produced isotopes to be used in the diagnosis of cancerous tumours. The isotope of potassium is injected into the body and collects in the tumour. Radiation is detected outside the person's body. It is a positron emitter with a half-life of almost 15 days. Explain why it's suitable for this procedure. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we can see that X is going to be a neutron. Because it's got a nucleon number of 1, but a proton number of 0, it must be a neutron. In this next one, we work out the change in mass between the particles before and the particles afterwards. So the change in mass given in the units is 5 times 10 to the minus 4 gigaelectron volts per c squared. So therefore the energy, E equals mc squared, so therefore the c squared cancels through. The energy is 5 times 10 to the minus 4 gigaelectron volts. We can then turn that into joules by multiplying by 10 to the 9 to get into electron volts, then by 1.6 times 10 to the minus 19 to get into joules, so it's 8 times 10 to the minus 14 joules. In this next one, positrons will annihilate with electrons in the body to produce gamma radiation. Now, gamma radiation from annihilation can penetrate out the body. Now, the half-life is long enough to allow the procedure to perform, but not too long to not give a large radiation dose to the person. The next question says, Radon-226 decays into Radium-226 decays into radon. Assume that 98% of the energy released in this process is converted to the kinetic energy of the alpha particle. Use the data below to determine the speed of the alpha particle. So pause the video now, then unpause the video when you want to go through your answer. Right, in this question, we can work out the change in mass by doing the mass before and the two masses afterwards and find the difference. So therefore, we find it to be 0.005229 U. We convert this into mega electron volts by using a bit of a cheat, multiplying by 931.5. We can then convert this into then joules by multiplying by 1.6 times 10 to the minus 13 because it's mega electron volts. So therefore, it's 7.8 times 10 to the minus 13 joules. So V therefore is going to be, well, E equals a half mv squared. So therefore, V is equal to the square root of 2 times by 0.98 E because it's 98% of the energy. So divided by the mass, so therefore it's 1.52 times 10 to the 7 meters per second. The next question says, the bismuth isotope decays by alpha decay to an isotope of thallium. Fill in the missing numbers for this decay. Then determine whether or not a kinetic energy of 3.6 megaelectron-volts for the alpha particle in the above reaction is consistent with the data below. The half-life of bismuth is 1.9 times 10 to the 19 years. Calculate the activity of 1 gram of bismuth. Then determine the number of nuclei in 1 gram of bismuth which will decay in 5 years. So pause the video now, then unpause the video when you want to go through your answer. Right, in this one we know that alpha is going to be 42 on the right hand side, therefore thallium to balance must be 205 on the top and 81 on the bottom. In this next one, what's the values going to be? Well, you find the masses of 83 protons and 126 neutrons for bismuth to be 210.7021 U. So therefore the binding energy, we can then work it through by then finding the difference. So therefore you get 164.83. Then subtract the mass defect for the bismuth mass. So therefore you can find the difference and you get 0.0039 U. Multiply that by 231.5 to get 3.63 mega electron volts. Then this next one, how do you work it through? Well, the half-life is log 2 over the decay constant, so pop in the values and you get 1.16 times 10 to the minus 27. The mass of one atom we know is going to be 209 times by the conversion factor into kilograms, so 1.6 times 10 to the minus 27. The number of nuclei is therefore going to be 2.88 times 10 to 21, so therefore our answer is going to be 3.3 times 10 to the minus 6 becquerels, and therefore we can work out how much decay in 5 years by using the values working through to be 525. In the next question, in the core of a main sequence star, nuclear fusion is converting hydrogen into helium. Explain the conditions required to bring about and maintain fusion in a main sequence star. A helium nucleus is a particularly stable nucleus containing 2 protons and 2 neutrons. Calculate the binding energy per nucleon in joules of a helium nucleus. Then the binding energy per nucleon of a helium is relatively large. Explain why this makes the helium nucleus particularly stable. So pause the video now, then unpause the video when you want to go through your answer. Right, fusion happens when there's a high enough temperature in the core, because this gives the protons a large enough kinetic energy, so the protons can get large enough to fuse because there's an electrostatic repulsion between the nuclei because they've got the same charge. You also need a very high density to maintain a high collision rate to maintain this fusion process, and that also leads to the high temperature. In the next one, find the mass difference before and afterwards. So you find the mass difference before and afterwards to be 28.1 mega electron volts per c squared. So when we say E equals mc squared, the c squared cancels through, so the binding energy is 28.1 MeV. So therefore we can turn that into electron volts by times by 10 to the 6, then times into joules by times by 1.6 times 10 to the minus 19. So it's 4.496 times 10 to the minus 12 joules. So divided by the number of nucleons that are in the helium, 4. So it's 1.124 times 10 to the minus 12 joules. Now the large binding energy per nucleon means that the energy required to remove the nucleus, the one nucleon from the nucleus is very large, so therefore it's very large to break apart it's very large energies are needed to break apart this helium nucleus, so therefore it's very stable. Now the decay products have a lower binding energy per nucleon, which means that it's less stable because you need less energy to separate it apart. The next question says, a nucleus of polonium-210 decays to lead-206 by emitting an alpha particle. The masses are shown in the table. Show that the energy released in the decay is about 9 times 10 to the minus 13 joules. 98% of the energy from the decay is released as kinetic energy of an alpha particle. Calculate the velocity of the alpha particle immediately after the decay, and explain why all the energy from the decay is released as kinetic energy of the alpha particle. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, what's the difference in mass? So you find the mass before, the mass afterwards, and it's 9.63 times 10 to the minus 30 kilograms is the difference. E equals mc squared, pop it through, 8.67 times 10 to the minus 1 joules. The next one, when you work it out, what happens through? So you'll take this value and you'll times by 0.98. That is therefore equal to the kinetic energy of the alpha particle, which is a half mv squared. You know the mass of the alpha particle from the information given, so you can say that therefore that equals equals a half mv squared. You can say v therefore is equal to the square root of 2 times by this energy over the mass, so it's 1.60 times 10 to the 7 meters per second. Now, why does not all of it get released as kinetic energy? Well, momentum must be conserved in this decay, so if the alpha particle has a movement, well, the lead nucleus must recoil to also counteract that, obviously in much slower speed because it's a much higher mass, so therefore it must take up some of the energy, of the kinetic energy of the reaction in that process. The next question says, alpha particle scattering led Rutherford to propose the nuclear model of the atom. Alpha particles were directed towards a thin gold foil. Describe how evidence from these experiments supports the nuclear model of the atom. So pause the video now, then unpause the video when you want to go through your answer. Right, it tells us that most of the particles are not deflected because they pass straight through the gold foil, which indicates that most of the gold atom is empty space. Some particles were deflected from their path by small angles. This indicates that there's a charge center to the atom with the same charge as the alpha particles. Then a small proportion were deflected through 90 degrees, they were backscattered, so most of the mass must be concentrated in this small point, which we call the nucleus. The next question says, radiographers commonly use molecules containing fluorine as traces in positron emission tomography scanning. Fluorine has a proton number of 9 and decays into oxygen by beta plus decay. Write the equation for the decay of a nucleus of fluorine using nuclear notation. The beta plus particle produced travels only a short distance in the patient before it meets an electron is annihilated. Calculate the wavelength of the gamma photons produced. Then X-rays and gamma rays are produced by different physical processes. Briefly describe both processes, and then fluorine has a half-life of 109.7 minutes. Explain the advantage that this has for the patient, but the disadvantage it has for the radiographers. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, the fluorine turns into the oxygen, and you've got your beta plus particle, and you've got your neutrino there to conserve lepton number. We know the nucleon number and the proton number are conserved before and afterwards. In this next one, E equals mc squared. So you've got the mass of the particle. It is the same as the mass of an electron because it's the antiparticle. So it's 8.2 times 10 to the minus 14 joules. E equals hc over lambda. So we know that from de Broglie and from and then you work it through to say, well, E equals hc over lambda, pop it all through and you get the value there, and then lambda therefore is 3 times 10 to the 8 over 1.2367 times 10 to the 20, so it's 2.42 times 10 to the minus 12 meters. Now, X-rays are formed when electrons de-excite and then release via gamma emission, whilst gamma rays come from the decay of the nuclei in the atom itself. Now, the advantage of having this half-life is that the half-life is short, so the exposure to the patient for ionizing radiation is kept low as possible, but the disadvantage is for the radiographers, they have a very short time to diagnose the patient from the information. The next question says, in 2023, a small capsule of cesium was lost from being transported from a mine in Western Australia. The activity of the cesium in the capsule was 19 gigabecquerels. Show that the decay constant for cesium is about 7.3 times 10 to the minus 10 seconds to the minus 1. Calculate the mass of the cesium in this capsule. Calculate the activity of the cesium in the capsule after 2 years. The capsule was found after 14 days. Calculate the total energy in joules released from the capsule in 14 days. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we know that the decay constant is log 2 over the half-life. Pop it all through. Half-life needs to be in seconds though, so therefore it's 7.31 times 10 to the minus 10 seconds to the minus 1. The mass we know well. Activity is equal to minus decay constant times by n. We know that for that n is therefore going to be the activity, which we know is to be 19 gigabecquerels, which is 19 times 10 to the 9, over the number of particles, over the decay constant, which is 7.31 times 10 to the minus 10, which is 2.60 times 10 to the 19. So therefore the mass is therefore going to be the number of molecules which you have times by 1.661 times 10 to the minus 27, because that turns into kilograms, so therefore it's 5.91 times 10 to the minus 6 kilograms. The activity after 2 years, well, we use the decay equation, A equals A0 e to the minus lambda t. We know the initial activity is 19 gigabecquerels, or 19 times 10 to the 9. We know what the decay constant is, and we know the time. Remember, after this, it has to be in seconds though, not years. So we work it through to be 1.81 times 10 to the 10 becquerels. And then this last one, we know that the energy is going to be equal to the activity multiplied by the time in seconds. So it'll be 14 times 86,400, because we're turning our days into seconds. Then we multiply by the energy released from one decay, which is 1.17 mega electron volts. So we get 6.96 times 10 to the 16 MeV. We can then convert that into joules by multiplying by 1.61 times 10 to the minus 19 times, get the mega up by times by 10 to the 6. So you get 4.30 times 10 to the 3 joules. The next question says, radium is a radioactive element. The most common isotope of radium has a half-life of almost 2,000 years. A sample of radium can remain at higher temperature than a surrounding for a long period of time. Explain how a sample of radium is able to release significant amounts of energy over a long period of time. So pause the video now, and then unpause the video when you want to go through your answer. Right, in this one, the rate of decay depends upon the number of unstable nuclei in the sample, because A equals minus decay constant times by N. Radium has a large half-life, so the unstable nuclei present are there for a long time. So when a nucleus decays, there's going to be a small decrease in the mass, and therefore when that happens, energy is released from the binding energy equation, E equals mc squared. Now, because the change in mass is small, C, 3 times 10 to the 8 squared, is still large, so a significant amount of energy is released. This energy released becomes the kinetic energy of the atoms in the sample, so therefore that links into the temperature of the sample, so the temperature is much higher of the sample compared to the surroundings. The next question says, in the early part of the 20th century, Rutherford made the first observation of an element being changed into a different element. Alpha particles were fired at nitrogen atoms. The nuclear equation for this reaction is shown. Calculate the minimum energy in MeV required for this reaction to take place, then calculate the minimum energy in MeV for this reaction to take place. So pause the video now, then unpause the video when you want to go through your answer. Right, so we know that the change in mass will be given by doing the mass of the products of this reactants before, subtracted the products of the decay afterwards. So we get 2.07 times 10 to the minus 30 kilograms from the information given. We know that the binding energy is mc squared, so we can then multiply that by c squared, so it's 1.863 times by 10 to the minus 13 joules. We can therefore say we can convert that into EV by dividing by 1.6 times 10 to the minus 19. So therefore it's 1.16 times 10 to the 6 EV, or 1.16 mega electron volts. Now, therefore we know that the momentum and energy must be conserved in a decay. So the products must have the kinetic energy after the reaction. So therefore it must be the same as it was before. So therefore you can work it through that way as well. So that brings an end to our revision session today. If we're being successful and we've learned in this revision session, we should be able to answer A-level physics examination style questions for nuclear physics, assess our understanding on A-level physics on the nuclear physics module, then understand what topics we need to improve upon for nuclear physics. So thank you so much for attending this revision session on nuclear physics for AQA A-level physics paper 2. Thank you so much and have a lovely day.